Every year, the world spends more than $20 billion on what seem like ordinary pieces of metal. Yet, these small pieces hold an invisible power that drives nearly every motor, turbine, and modern device. Behind their simple metallic look lies a world of material science, atomic precision, and human mastery. From deep mines, where rare earths are found, to blazing furnaces that forge invisible force, every step tells a story of transformation. These metals are more than just materials, they are the hearts that make technology move. Every smartphone, every electric vehicle, every wind turbine depends on them silently doing their job. So, how are these powerful magnets born? And how does China control almost all of their production? Today, let's journey inside the hidden factories where metals turn into force, and that force powers the future of humanity. The story of a magnet begins far beneath the Earth's surface, in mines rich with rare earth elements like neodymium, iron, and boron. Geological engineers survey the rocky layers, searching for veins that hide these precious materials. When a suitable deposit is found, controlled explosions carefully break the rock without shattering the valuable ore. This precise blasting ensures that the minerals remain intact, protecting their purity and magnetic potential. Unlike iron mining, where destruction is massive, rare earth mining is slow, surgical, and exact. The extracted ore is carried by conveyor belts and heavy trucks to the sorting yards. There, workers separate and label different types of ore, preparing them for cleaning and grinding. Safety is critical because rare earths sometimes contain traces of uranium or thorium. Dust and gas levels are constantly monitored, ensuring a safe and clean extraction zone. Once cleaned, the ore enters the milling section where giant ball mills crush it into fine particles. Inside the rotating drums, the grinding speed stays between 20 and 30 revolutions per minute. For jet mills, air pressure is maintained at nearly 100 pounds per square inch, creating intense turbulence. After 4 to 6 hours, the ore turns into a fine powder just a few microns wide. Temperature control is vital. It must stay below 180 degrees Fahrenheit to preserve the crystal structure. Once cooled with inert gas, the powder passes through layered screens to separate particle sizes. The next phase, flotation, separates valuable rare earths from waste rock. The powder mixes with water and chemicals, creating a liquid slurry filled with bubbles. When air is pumped in, the rare earth particles stick to the bubbles and float to the top. Impurities sink to the bottom, leaving behind a concentrated layer of neodymium, samarium, and iron oxide. Because rare earths occur in low concentration, this step demands absolute precision and chemical balance. The sealed tanks use dust collectors and control systems to prevent toxic leaks during flotation. Once purified, engineers analyze each batch for moisture composition and element ratios. For neodymium magnets, the recipe mixes neodymium, iron, and boron in perfect proportion. For ferrite magnets, the blend includes iron oxide with barium or strontium. Each powder is sealed from air to prevent even a trace of oxidation before melting. Inside induction furnaces, the atmosphere is replaced with argon gas, creating a pure vacuum. The temperature slowly rises to nearly 3000 degrees Fahrenheit, melting the metals into a glowing liquid alloy. After 2 to 4 hours, the molten mixture is poured onto a fast spinning drum to cool instantly. This rapid cooling solidifies the alloy into thin flakes, locking in a fine and uniform crystal structure. The solidified flakes are ground again inside inert gas chambers, forming a dark gray ultrafine powder. The powder is placed in steel molds exposed to powerful magnetic fields several Teslas strong. Each particle rotates and aligns in the same direction, like countless compass needles finding one pole. With perfect alignment, the powder is pressed into solid blocks called magnetic blanks. These blanks are heated inside vacuum furnaces at around 2400 degrees Fahrenheit for hours of sintering. The heat bonds the particles tightly, removing all internal gaps and turning them into dense solid metal. Controlled cooling follows, degree by degree, to preserve the internal magnetic orientation. Then, secondary heat treatment at about 950 degrees Fahrenheit stabilizes the entire structure. The hardened magnets are cut and shaped with laser or diamond tools to achieve exact dimensions. To prevent corrosion, each magnet is coated with nickel, zinc, or epoxy, creating a protective shell. Finally, in the magnetizing stage, an electrical pulse of up to 3000 volts charges the blocks with magnetic life. Every magnetic domain inside aligns instantly, turning lifeless metal into a true magnet with north and south poles. From there, each magnet is tested, packed, and sent to power electric cars, wind turbines, robots, and the invisible heartbeat of modern civilization.